Today I'd like to talk about how Chain Framework integrate with R2, and mostly I will focus on the details I didn't cover in my last HITB talk. If you didn't watch that talk, never mind. I will do a fast recap. So first of all, the recap in the last ETV AMS 2021, I did a talk on when chilling meets radar 2 and how we implement our symbolic execution based on radar 2 and the chilling framework. And today I'd like to focus on some interesting details and mostly the black magic behind the whole thing. So fast recap of Chilling framework. Chilling provides almost the best dynamic instrumentation experience. For example, it's system simulation and you have flexible hook and snapshot and have full control of the sandbox. And so what's next? So we think for a long time what's the next of Chilling framework, and our answer is we have to expand the ability to analyze both dynamic analysis and static analysis, and the best solution is to R2 since it's free. The free software is open source and it's the best alternative, not anti-Python. So our first demo is symbolic execution. So about R2, R2 is a Swiss snap of the reverse engineering, and it and but it also has almost the steepest learning curve. You have to learn different commands, and sometimes the source is your best friends. As often the case, I have to read the parser to know which command I need. But you could find almost everything, yes, everything you need for security analysis. For example, you want to disassemble some instructions, you want to show the control flow, and you could debug. And it also has tons of utilities. For example, the question mark is my favorite, and what we chilling team really focus on is the ESL, the Evaluable Strings Intermediate Language, and it uses reverse polish notation and designed for interpretation and suitable for symbolic execution. So first of all, R2 is written in C language, and the chilling is written in Python language. So there needs a bridge, and the existing solution is R2 pipe and R long. R2 pipe was the only available Python binding at that time, but it requires rather to be installed system wide, and we hope to minimize the chilling installation to pip install. So we don't want user to execute various commands to just to install a dependency. So so the R2 not suitable for the direct use. Along with the other way is running a Python interpreter in R2, and it seems good, but we expect to run standalone, and it's still system-wide R2 installation is required. So I decided to reinvent the view. So I wrote a brand new Python binding for R2 bar. So how it works, R2 headers is clean enough to do auto generation for almost every API is marked with R API, and the bindings are generated automatically with CTAP sleep and the GitHub CI. So in this talk, I would cover the detail of this part. So go next. So actually how it works, we have C header from Radar 2, and we expect Python C type bindings, and the 2 is C type lib 2. It's backend by libclone, and it parses the C header and up to the AST, and produce the Python script from the AST. But it's not actually maintained. It has many bugs, and for example, there are many issues I raised to fix some bugs which prevent the generation, and that's all. So with the bugs fixed, we could generate the Python bindings seamlessly. No. So let's see the real black magic. First off, RU2. Unlike other R2 modules, it is managed by multiple headers. There are no R2 API in the header file. As you can see, it includes RU2, REvent, R assert various subheaders. But so CTabsly won't generate symbols in included headers. or for example, some if it do generate symbols in the included headers, the headers like stdio and std will be also generated. So syntax won't generate symbols in included headers. So what's my solution? I do the expansion manually like the standard C preprocessor, and I apply C tightly on expanded header. For example, here as you can see, I generated a brand new header r2con2021-lazymio-symex-and-further. It is composed of all these headers. Just copy their content to these headers by the sequence, and you get this big file and generate all symbols from this file. So that's still enough. We still have more black magic. So after we generate the bindings, we have to put everything together. Unfortunately, syntax is designed to output a single script. For example, you have a header, you have a source file. It just generate that script, and you can only use with that script. But we would like elaborate. We want just for example, you import bar and you get everything. So we have to try to put everything together. So my solution is to mangle output by regular expression. Yeah, it's 30. I know it's 30 indeed, but it works. Basically, this is the only way I could think about that could solve the problem, and it gives each R module a separate namespace, and I remove the local path generated. For example, my local path generated and make it relative, and I write a wrapper to use the relative path to load all R libs. So the last black magic, is Mason. Oh, you may not imagine what's the problem with Mason. So first of all, we would like the cross-platform, so I choose Mason, but it has very critical bug on macOS. Here I give a link, but basically, in summary, you can't use relative paths to refer dynamically on Mason built libraries. So it's really frustrating. I tried many times, and finally I found it's a bug of Mason. So what's my solution? And another black magic. I parse the libraries. It's macro files, and rewrite the downloader path. So it's the last black magic, and put all these black magic together. What you get? A working R2D bar, a passive bindings. So that's R2D bar. And next, I will cover some details about how the symbolic execution implemented. So I skip the concept, and I skip the concept and demo. If you are unfamiliar with this part, you could go to the HITB YouTube channel and saw my demo and some concept introduction. So for today's talk, I just start from the difficulties, so I could introduce the details. So first of all, the implementation is much complex than expected. R2 itself doesn't have memory rewrite implemented, so we have to do it our own. And also, we can't use R2 registers implementation due to we have to store symbolic values, and as a result, we did a full re-implementation of ESL. No, not all. The R2 is still responsible for the design, but the interpreter is implemented by our own, and it may become another emulation engine to replace Unicorn. I will discuss this later. And the symbolic execution is never a silver bullet. Sometimes it's really slow since you have to keep every state immutable. Also, I know there are many things to optimize, but in theory you have to keep each state, and the state would be exploded for a complex function and make it acceptable slow. So let's see some details. First off, the memory. So why would I would like to re-implement the memory? Since we would like the memory that holds symbolic values, and it should support full clone since the memory, a memory object or a memory of a state should be immutable, and it should support a memory map and a map, and the implementation. So the memory itself is managed by segments. So every I mean, you couldn't just allocate a very long array and allow user to write values. You have to use segments every time user writes to an address. You allocate a new segment, just like the page tables, but I implement a simpler version. So it's managed by segments. Every time user writes to an address, you create a segment and insert to current segment array. And it's really complex than expected. For example, when I insert a segment, I have to check the overlap segment and merge it segment, or delete some existing segment and replace it with a new one. So it's really complex. And the second implementation is the register implementation. Again, the reason is that we would like the register to hold the symbolic values, and it also should support full clone, since we need an immutable copy for each state. But fortunately, it's much simpler than memory. And the most importantly, we do a full implementation of the ESL interpreter. So first of all, since we have implemented the memory and registers, so it's impossible to use R2 implementation. And in our implementation, the most important part is how we handle symbolic values when we encounter a branch. When we here is the code snippet. When we encounter a branch, for example, if here we we add the conditions to the we add the condition. For example, here source doesn't equal to 0, and then after we interpret this macro code, we search the possible PC. For example, we just add the condition of the true. In this function, we could search whether it could be false or other branch. So in this case, ESL solves really a nice reference, and I learned many symbolic execution knowledge from the ESL to solve, and still we do our unique optimization on our side. So for future, you may ask, wow, you gave the talk on symbolic execution 3 months ago. Why you still don't make it public or open source? So basically, the symbolic execution is still in heavy development, and what I was doing is Unicode 2. Yes. So in order to release the symbolic execution, we are waiting for the Unicode 2 to be released, and then we may have the engine module, and we can introduce ESL as a new engine, and then we can implement the symbolic execution based on the ESL, and then we have the a better collection of the extension. And you could and for the future steps. Sorry, I have a typo here. This is the future steps. Firstly, we just release the EVM, and I'm working on Unicode 2. Yeah, it's a brand new version of Unicode 2. Now, not only I add some, not only it is bumped to higher QMU 5. Unicode is originally is based on QMU 2, which is quite old, and Unicode 2 is based on QMU 5, and also I add very a lot of exciting features, and also yeah, our chilling team recently is working on some secret projects based on UC2 and its new features. And then after we release UC2 and then release this secret project, and we are going to introduce ESSL as an alternative engine to Unicode, I mean. And after that we could introduce the rest of R2 components to for example implement symbolic execution and various stack analysis. So that's all the future steps. And last for credits, so first off, the Radar 2 for the next project, and synthetically for R2 Libar implementation is also for the reference, and Anchor for the design reference, these three for the excellent solver, and Pancake for the template help. So that's all. Thank you.